Most likely one of them. They have very long exposure of 3I Atlas, but in all cases, it has nothing to do with the cylindrical shape.
A comet from deep space just buzzed past Mars, and the planet glowed green. Instruments spiked. A rhythmic hum echoed across space. Then came the weird part: a spiral breakup, a methane surge, and a pulse that won't stop. NASA says it's natural. Others aren't so sure. What really happened when 3I Atlas arrived? The approach. For weeks, every major space agency on Earth had one name pinned at the top of their screens: 3I Atlas. The object was already known as the third interstellar traveler to enter our solar system, but now it was racing toward a narrow encounter that had astronomers holding their breath. On October 3, 2025, the comet would pass within 18 million miles of Mars, its closest approach to any planet before disappearing back into deep space. Unlike Earth, Mars offered a clean, unobstructed laboratory. No clouds, thick atmosphere, no radio interference. Every camera and spectrometer orbiting the red planet was tuned to watch. For the first time in history, humanity would observe a visitor from another star through the eyes of machines already stationed on another world. The preparation bordered on military precision. At NASA's Jet Propulsion Laboratory, engineers spent sleepless nights recalibrating instruments aboard the Mars Reconnaissance Orbiter. Its Horizon camera could capture features down to 100 feet per pixel, just enough to resolve a faint smear if the comet brightened. MAVEN's ultraviolet spectrograph was reconfigured to record potential bursts of ionized gas around the event. Across the Atlantic, the European Space Agency synchronized its own fleet: Mars Express with its Omega and SPICAM spectrometers, and the ExoMars Trace Gas Orbiter, armed with the Nomad and Cassis instruments. China's Tianwen-1 probe and the United Arab Emirates Hope Orbiter joined in, creating the most extensive interplanetary observation network ever assembled. Even ESA's JUICE spacecraft on its way to Jupiter was placed in a standby mode to catch distant readings of solar wind variations during the flyby. Down on the Martian surface, Perseverance wasn't built for astronomy, but its Mastcam Z cameras were aimed skyward. The rover's environmental sensors were reprogrammed to monitor for charged particle surges, magnetic tremors, and electrostatic shifts that might ripple through the thin air as the comet passed. On Earth, the excitement had the feel of a global countdown. Ground observatories, Gemini South, Hubble, the Vera Rubin Observatory, lined up coordinated exposures just before the comet slipped behind the sun. Universities ran simulations predicting dust tails, gas production, and brightness curves. But something was already odd. 3I Atlas's magnitude wasn't following projections. Its glow fluctuated unpredictably, hinting at volatile behavior even before reaching Mars. NASA's official forecast called for a moderate outgassing event. Privately, some mission scientists worried it could flare brighter than expected and blind delicate sensors. MRO's imaging teams drafted emergency exposure protocols in case the nucleus erupted. The phrase "controlled chaos" popped up more than once in internal chat logs. Then came the complication no one wanted: politics. A federal funding lapse threatened NASA's public data pipeline just as the encounter window opened. With much of the agency operating in safe mode, updates would have to pass through slower European or academic channels. The timing couldn't have been worse. Despite the bureaucratic turbulence, the operational side pressed on. On October 1st, all active orbiters entered their comet tracking sequences. Telemetry rolled through the Deep Space Network, calibration files were verified, and pointing commands fired across tens of millions of miles. By October 2nd, Mars was a world holding its breath under the gaze of a sky filled with instruments. In the control rooms, California, Darmstadt, Beijing, Dubai, the mood was sharp and quiet. Screens glowed with countdowns. Teams swapped data in real time through encrypted links. Every bit of hardware was synchronized to the millisecond. They didn't know what to expect. Most comets behave like clockwork: ice, dust, sunlight, vapor. But 3I Atlas wasn't one of ours. It came from elsewhere, carrying chemistry no one had ever seen up close. What if its materials reacted violently to solar radiation? What if it broke apart prematurely? What if nothing happened at all? In those final hours before the pass, one thought echoed in every mission log. We're about to watch an alien object pass a living planet. Whatever followed, the cameras were ready. The night Mars glowed green. At 4 a.m., UTC, October 3rd, 2025, the moment everyone had been waiting for arrived. 3I Atlas slipped into its closest pass with Mars, just 18 million miles away, and the red planet lit up like no one had ever seen before. It began quietly. Orbiters registered a faint uptick in reflected light. Then, all at once, the comet's coma expanded. It didn't just grow, it swelled, a glowing sphere that doubled in apparent diameter within minutes. Spectrographs from MAVEN and Mars Express caught the sudden surge, their detectors saturating before technicians could adjust exposure settings. The signal screamed one color more than any other: green. The hue wasn't cosmetic. In spectral terms, it was the signature of diatomic carbon, a molecule that fluoresces bright green under solar ultraviolet radiation. Most comets show a touch of it. 3I Atlas was drenched in it. The emission line ratios were off the charts, hinting at a chemically aggressive surface, venting faster than models predicted. From orbit, Mars looked like it was bathed in a soft jade fog. Within the thin Martian sky, the effects rippled fast. MAVEN's imaging ultraviolet spectrograph picked up UV flashes skipping across the planet's night side. Short bursts, each lasting less than 2 seconds, rolling like distant lightning. They weren't meteor trails or instrument glitches. Their timing matched pulses in the comet's expanding coma, suggesting a cascade of charged particle impacts in the upper atmosphere. ESA's Mars Express confirmed the view from another angle, ultraviolet curtains stretching along localized arcs, particularly above the southern highlands. Those curtains brightened, faded, then reignited, as if responding to invisible tides. Scientists on the control loops called them rogue auroras. The term stuck. Down on the surface, Perseverance kept its sensors fixed upward. The rover couldn't see the colors with its human-style cameras. The night was too dark, but its radiation detectors caught tiny rhythmic spikes in particle counts. The spikes came every few seconds, rising and falling like the echo of some distant engine. The cause was natural, but the pattern was mesmerizing. Even Mars seemed to hum in time with its visitor. For about 40 minutes, the planet's upper atmosphere shimmered in wavelengths humans had never associated with Mars. Green, teal, violet, ghostly shades that made no meteorological sense. To anyone looking from the surface, it would have felt like standing under a silent storm of light. Telemetry poured in. Temperature gradients in the upper atmosphere shifted by measurable margins. Electron densities jumped, and the magnetometer on MAVEN logged a temporary distortion, minor but sharp. The readings implied that 3I Atlas's tail, thick with ionized gas, had brushed Mars's magnetic remnants, briefly coupling the two environments like an electrical handshake. Then, almost as suddenly as it began, the spectacle faded. The auroras dimmed to faint ghost arcs. The green glare drained from the coma as the comet continued on its path. Within an hour, Mars returned to its usual rusty silence. But the sensors told another story. A planet momentarily energized, pulsing with static that took hours to dissipate. In mission control rooms, there was no applause, just quiet disbelief. NASA's report called it a transient atmospheric excitation event. ESA's note described unexpected ultraviolet resonance. Both were careful phrases, the scientific equivalent of "we don't know yet." Among engineers, one line kept surfacing in private chat threads: Mars glowed. It wasn't a metaphor. The planet, for those brief minutes, radiated energy in colors it rarely owns. By the time the last data packets arrived through the Deep Space Network, the comet was already tens of millions of miles farther along its trajectory. The spectacle had ended, but something about it lingered in every mind watching the screens. The data could be analyzed later. For now, one truth cut through the static. For the first time, Mars had shone in green light born of another star, the spiral breakup. When the last of the auroral glow faded from Mars, the orbiters turned their gaze back toward the comet itself. What they found in the hours after the flyby rewrote every assumption about how comets die, or perhaps how they live. High-resolution imagery from NASA's Mars Reconnaissance Orbiter began coming down first. The HIRIS camera, pointed toward the receding 3I Atlas, revealed a subtle but unmistakable distortion in the comet's outline. The once solid nucleus now appeared fractured, shedding material in what should have been a chaotic spray. Instead, the fragments formed curving arcs that wrapped around the primary core like strands of a helix. Comet fragmentation is old news. Heat, spin, and tidal forces can crack even large nuclei into shards. But this wasn't random dispersion. It was patterned, deliberate-looking, almost graceful. The arcs seemed to rotate around the core in slow synchronization, as if invisible threads were keeping time. When the images from ESA's ExoMars Trace Gas Orbiter and Mars Express arrived hours later, they confirmed the same geometry from different angles. 5 distinct fragments, each roughly 1 to 3 miles wide, traced spiral tracks in perfect phasing around the main body. The motion couldn't be explained by normal physics alone. Dust jets could spin a fragment, but not choreograph it. Solar radiation could scatter debris, but not align it so cleanly. Scientists proposed theories as fast as they could type. One camp argued that rotational instability caused symmetrical shedding, a nucleus spinning fast enough to eject chunks along predictable vectors. Another camp countered that the spiral shape suggested a magnetized plasma environment, guiding the fragments along field lines rather than pure momentum. But even that required an internal magnetic field strong enough to rival a small asteroid. No known comet had one. Then came the signal. At 4:47 UTC, Mars Express's radio science experiment picked up a low-frequency hum, repeating every 22 seconds. The amplitude was faint, barely above background, but the rhythm was unmistakable. It wasn't random cosmic noise. A minute later, the ExoMars TGO registered the same periodic pulse from a completely different orbit, half a planet away. Engineers tore through every checklist: instrument feedback, timing drift, telemetry echoes. The signal persisted. 2 spacecraft, 2 independent systems, both detecting the same periodic pulse with identical timing. For nearly an hour, the beat continued before fading into static. The official line wrote it off as a plasma resonance, an interaction between the charged tail of 3I Atlas and the patchy magnetism of Mars's crust. But off the record, scientists whispered a different word: modulation. The pattern was too clean, the spacing too precise. Even the background noise seemed to dip in sync with the pulse, as if responding to it. NASA's public report kept its tone clinical. Observed periodic signal consistent with transient plasma oscillation. No evidence of artificial origin. Behind closed doors, a senior systems engineer emailed one line that later leaked. 2 instruments, 1 frequency. Space doesn't hum in time by accident. For scientists who had spent their careers watching dust and ice behave predictably, 3I Atlas had turned into something uncomfortably alive. A comet that spun, shattered, and sang to itself in perfect rhythm. When the data packet stopped and silence returned to Mars orbit, No one claimed to understand what they had just seen. The only consensus was simple and unnerving. Whatever 3I Atlas was, it didn't just break apart, it performed. The methane mystery. When the last images of 3I Atlas finished transmitting, mission control teams thought the excitement was over. But then, deep in the stream of spectroscopic data from ESA's ExoMars Trace Gas Orbiter, something appeared that stopped the analysts cold: a methane spike in the upper atmosphere of Mars. Methane on Mars has always been the planet's biggest enigma. Since the early 2000s, instruments had occasionally caught fleeting traces of it, thin plumes that came and went without pattern. The gas shouldn't last long in the Martian environment. Sunlight and oxidants rip it apart in months. Yet there it was again, this time far stronger and timed with eerie precision. The increase started just hours after 3I Atlas's close pass and peaked in the following orbit of TGO, roughly 10 hours later. Normally, the orbiter detected background methane concentrations at less than 10 parts per billion. The new readings showed a jump of more than 5-fold, spanning a narrow latitude band around the Martian equator. That kind of change couldn't be a random fluctuation. And unlike previous detections, this one came from multiple instruments. NOMAD and SpyCam both confirmed the same spectral signature. It was unmistakable. The first question was obvious. Did the comet seed Mars with methane? Some scientists argued yes. They pointed out that 3I Atlas carried volatile ices rich in exotic carbon compounds, including cyanogen and CO2. If fragments or microscopic grains entered the upper atmosphere, even for seconds, they could have released trapped gases on contact with solar radiation. A cometary source would explain the sharp rise and the rapid decay that followed. But another camp, led by several MAVEN researchers, wasn't convinced. They proposed that the comet's charged tail and the energetic particles it dragged through the Martian magnetosphere could have acted like a trigger, jolting subsurface reservoirs of methane that were already there. According to this theory, the comet didn't deliver new gas. It woke up dormant chemistry locked beneath the regolith. There was precedent for that idea. Years earlier, short-lived methane bursts had been correlated with electrical discharges in Mars' thin atmosphere. Static storms invisible to the naked eye. If the 3I Atlas encounter created an electromagnetic pulse strong enough to rattle the crustal fields, it could have briefly opened microfractures where ancient methane had been trapped for centuries. Either scenario was revolutionary. One involved extraterrestrial deposition, the other Martian reactivation. Both challenged decades of assumptions about the planet's chemistry. Data reduction continued around the clock. Researchers cross-checked calibration files, searching for any sign of instrument contamination or line misidentification. Nothing fit. The spectral lines of methane at 3.3 microns stood clear as day, flanked by faint side bands of ethyl radicals and CO fragments, consistent with a natural carbon-based source. When NASA finally released a joint statement with ESA, the language was cautious. A transient increase in atmospheric methane was observed, coincident with the passage of interstellar comet 3I Atlas. The source of the anomaly remains under investigation behind the scenes. That phrase, coincident with the passage, was the understatement of the decade. The timing wasn't just coincidental, it was precise to within minutes. Independent teams later compared the methane spike with solar wind data and found no solar event that could explain it. Mars hadn't been hit by a flare, nor a coronal mass ejection. The only major variable in play was the comet. For weeks afterward, laboratories on Earth modeled the chemistry. Could 3I Atlas's exotic dust, enriched with interstellar organics, have catalyzed a reaction when mixed with Mars' thin carbon dioxide atmosphere? Could its plasma tail have created ionospheric lightning, breaking molecules apart and recombining them into methane? Each theory came with equations but no certainty. The numbers remained stubbornly poetic. One interstellar visitor, one brief encounter, one impossible spike. Officially, the event was labeled a transient methane anomaly. Unofficially, scientists had a simpler name for it: the breath of Mars, the data that vanished. In the hours after 3, I-Atlas swept past Mars. The scientific world waited for a flood of data that never came. The orbiters had watched history unfold. The rovers had recorded every twitch in the air. But as Earth turned toward the new day, the official channels went quiet. It wasn't a malfunction. It was politics. The U.S. government shutdown that began days earlier had frozen NASA's public communications. Websites went into standby mode, dashboards stopped updating, and live telemetry feeds were locked behind internal servers. For the first time in decades, the world's leading space agency had a front-row seat to a cosmic event and couldn't say a word about it. ESA, immune to Washington's bureaucracy, pressed forward. Their official statements confirmed successful operations from Mars Express and the Trace Gas Orbiter, but the language was careful, sanitized, and vague. Preliminary data indicate transient atmospheric and spectroscopic activity coinciding with 3 I-Atlas's passage. No images and without answers. Into that silence stepped the amateurs. Around the world, astrophotographers and data enthusiasts dove into public archives, stitching together whatever scraps they could find. One of them, Simeon Schmaus, noticed something peculiar in Perseverance's Mastcam Z feed, a faint moving blur visible across a handful of night sky frames taken on October 2nd. After stacking 20 images, he found it again, a small streak cutting against the motion of the stars. He posted it with one line: "I think Perseverance may have caught 3 I-Atlas from the surface." That single post detonated across the internet. Reddit threads exploded. YouTube channels spun up analysis breakdowns, and social media went feral with speculation. Some users treated it as a historic first, the first interstellar object ever imaged from the surface of another planet. Others saw something deeper, framing it as the first glimpse of a machine wearing the mask of a comet. Loeb didn't claim it was artificial, but his tone was unmistakable. Either this is the most extraordinary natural coincidence in modern astronomy, or something guided it. That line hit headlines faster than any data packet from Mars. In the vacuum left by NASA's silence, conspiracy culture bloomed. Anonymous accounts posted fabricated leaks, claiming hidden radio transmissions or encrypted rover messages. Clickbait headlines screamed, "NASA hiding alien artifact," before the science community could even log on to refute them. Inside the real mission teams, there was only exhaustion. Engineers, still pulling 20-hour shifts, watched their work twist into sensationalism, while their actual data sat embargoed behind federal protocols. "We're not hiding anything," one Mars reconnaissance engineer vented on a private forum. "We're just not allowed to hit send." By the time partial communications resumed days later, the world had already moved from curiosity to conspiracy fever. The narrative had mutated. 3 I-Atlas wasn't just a comet. It was a message, a probe, a test run. Every missing image became proof. Every delayed statement became confirmation. ESA's slow, steady reports couldn't compete with that wildfire. When NASA's official channels finally reopened, they published a 2-line update. All Mars spacecraft remain healthy. Preliminary data on Comet 3 I-Atlas is under analysis. That was it. After the most unusual comet pass in human history, the agency said nothing more. And so the question spread faster than any signal from Mars. Did NASA lose the data or choose not to show it? The Sun test. By mid-October 2025, the red planet had slipped far behind, and 3 I-Atlas was racing toward the Sun like a bullet on fire. Its next milestone, perihelion, the point of closest solar approach, is scheduled for October 29th. In astronomical terms, the comet was heading straight for a trial by heat, and the world was watching. Every interstellar object that's entered our solar system before had gone silent by now. Oumuamua had passed too fast to observe in detail. Borisov had behaved like an ordinary comet, but 3I Atlas was different, larger, brighter, and strangely resilient. Instead of fading as it neared the sun, its luminosity was increasing, outpacing predictions by nearly a full magnitude per week. At 1.36 astronomical units, or roughly 126 million miles from the sun, the comet should have started breaking apart. Solar radiation pressure, tidal stress, and volatile outgassing were supposed to peel its surface into dust. Yet, photometric models showed the opposite. The nucleus held its shape. Its coma, the gas envelope surrounding the core, expanded evenly, showing no sign of fragmentation. To the European Space Agency, this was the perfect setup for a live experiment. The Jupiter Icy Moons Explorer, still months away from its main mission at Jupiter, was in an ideal position to observe. Engineers reoriented its instruments to watch 3I Atlas from afar. Over a 3-week observation window, JUICE would measure infrared spectra, dust polarization, and thermal emission curves. The goal: determine if the comet's composition matched anything known from our solar system. Meanwhile, astronomers on Earth used what limited geometry they had left. The comet was already lost in solar glare, visible only to the SOHO and STEREO solar observatories. Through their cameras, scientists tracked a bright emerald filament stretching millions of miles behind the nucleus. The green hue, likely from diatomic carbon, was familiar, but the structure wasn't. The tail didn't fan outward as expected. It remained tightly collimated, like a beam. Theorists began arguing in journals and live streams. One camp insisted that 3I Atlas's structural integrity meant it was made of hyperdense ices, frozen under extreme interstellar pressures. Others proposed an unusually high metal fraction, perhaps a crust of nickel iron shielding its volatile heart. A more daring minority floated the unspoken idea that its stability hinted at design, not chance. No one could deny the odds. The comet's orbit was nearly aligned with the ecliptic plane of the planets, an alignment with a random probability of just 0.2%. By late October, thermal readings suggested surface temperatures above 700 degrees Fahrenheit. Any ordinary comet would have disintegrated into a cloud of debris by now. Yet spectra from JUICE showed stable absorption bands, no explosive mass loss, and runaway vapor jets. The object was enduring the solar onslaught with unnerving calm. Around the world, observatories prepared for the moment it would swing around the sun and re-emerge on the other side. Would it survive intact? Would it explode in a flash of alien dust? Or would it do something no model could predict? Scientists used one term repeatedly: the stress test. If the comet were ordinary, this was the point where it would fail. If it wasn't, the sun itself would tell the truth. On the eve of perihelion, telescopes from Hawaii to the Canary Islands tracked the faint halo disappearing into the solar corona. The comet was now invisible, swallowed by light. For 48 hours, nothing came through. No images, data, only silence and static. Then, as the solar glare began to thin, a single bright speck reappeared on the far side, brighter than before, steady, intact. Against every calculation, 3I Atlas had survived the sun, the signal that stayed. When the comet emerged from the solar corona, it was not the tattered ruin scientists expected. It was bright, symmetrical, and eerily stable. Its coma shimmered like a green ember against the black backdrop of interplanetary space. Survival alone would have been headline enough, but within days of its reappearance, another phenomenon began to surface. Faint, rhythmic radio oscillations coming from the comet's general direction. The first detection came from the Parkes Observatory in Australia. The signal was subtle, a nearly inaudible modulation hidden inside natural solar background noise. What caught attention wasn't its strength, but its regularity. One pulse every 22 seconds. At first, no one wanted to believe it. The 22-second rhythm had already shown up in Mars data weeks earlier. Most had dismissed it as plasma resonance between the comet's charged tail and the Martian crust. But now Mars was millions of miles away, and the same pattern was returning, this time in open space. Independent confirmation came quickly. Arecibo's successor facility in Puerto Rico and the Green Bank Telescope in West Virginia both logged identical patterns. Even radio amateurs with high-gain dishes reported weak echoes matching the same interval. When plotted together, the pulses lined up with almost atomic precision. Scientists scrambled for natural explanations. Solar wind turbulence, magnetohydrodynamic waves, cosmic ray modulation. Every theory was tested and discarded. The signal's frequency drifted minutely, but always snapped back to a steady beat. It wasn't broadcasting information. It was simply there, steady as a clock buried in static. Meanwhile, optical observatories noticed something else. The comet's brightness fluctuated faintly in the same rhythm, not enough for the naked eye, but measurable in photometric data. It was as if the nucleus was breathing, pulsing with light in time with the invisible hum. To the cautious mind, the cause was clear: a natural outgassing cycle tied to the comet's rotation, modulating both luminosity and plasma density. By mid-November, the phenomenon had a name: the Atlas Beat. It spread beyond scientific circles, leaping into popular culture. Music producers sampled the signal and wove it into tracks. Podcasts debated whether it was an artifact or a message. News outlets ran headlines like, "The Comet That Keeps Time." Inside observatories, the mood wasn't excitement. It was discomfort. Researchers knew they were staring at something outside familiar categories, yet too ambiguous to claim as artificial. No pattern of encoding, language, just the quiet tick of cosmic metronomy. When ESA's JUICE spacecraft passed through the comet's magnetic wake, its instruments briefly registered a faint electromagnetic surge matching the same period. Then, nothing. The comet continued outward, sailing away from the sun with unshaken brightness, its tail streaming in a perfectly coherent line. On Mars, months later, MAVEN's ultraviolet spectrometer detected a tiny echo of that same periodic modulation in the ionosphere, a ghostly afterimage of an encounter that had already passed. The planet seemed to remember. By December, 3I Atlas was climbing out of the inner solar system, fading beyond the reach of most telescopes. Yet the 22-second pulse persisted, weaker now, but still traceable. The rhythm felt like a signature, or perhaps a farewell. Historians will argue about what it meant. Physicists will write it off as a coincidence wrapped in pattern recognition. But for those who watched the data unfold in real time, it left an indelible impression. The universe had spoken in time, not words. 3I Atlas left behind neither debris, danger, nor proof. Only a question, still pulsing faintly across space. Every 22 seconds, the cosmos seems to ask, "Were you listening? Thanks for watching." If 3I Atlas's Mars encounter blew your mind too, hit like, subscribe, and share. More unbelievable space discoveries are coming soon. Stay tuned for what's next.